Hello, everyone. This is the first unit that I mentioned over and over because it's very difficult. And I also in weekly reading list asks you to refresh your proving skill, how to prove something being correct. So this unit and the next unit would be extremely difficult to some of you who are not used to proving something or arguing in a rigorous way. If you fail to do that, then you have to be very careful. As I mentioned to you, you are welcome to create Zoom meeting with me in person or several people that join the same meeting. And this is about synchronization. Synchronization is the most difficult topics in this semester. And these two units focus on the sort of theoretical part, and then we focus on the practical part. In this unit, we are going to talk about two important concepts: critical section and the mutual exclusion. Possible topics throughout this semester will be: one, why is synchronization needed? And followed by race conditions. To handle race conditions or avoid race conditions, we need a concept called critical sections. To create a critical section, we need the help from software to solve this problem. Or if hardware can support it, we use hardware. But for most of time, we use some system supplied mechanisms, mostly semaphores and monitors. Now, between the discussions of semaphore and monitor, we have one more section. We call it how to catch race conditions. You have heard the word race conditions a couple times. It is something we try to avoid. It is also something extremely difficult to catch. So we have one section here showing to you how, to the best of my knowledge, to find race conditions in your program. Now, look at this example. Let's start with processes. We have two processes, process 1 and process 2. We have probably just a shared memory in which we store the array A with 3 elements. Initially, the value would be 3, 4, and 5. Okay, so process 1, it's A0 and A1 together. The result would be saved to A1, which modifies its original value. For process 2, it takes the value in A1 and A2, computes the sum, and saves the results back to A2, overwriting the original value. So now we have one global entity, two processes. Just assume that these two processes has two simple statements. So the question is, what will be the results after process 1 and process 2 finish their instructions, their execution? We know A0 is never modified. See, we only modified A1 and A2. We never modify A0. So we know at the end of process 1 and process 2, A0 has to be 3. But what are the values for A1 and A2? Why I ask this question? You may want to say CK is stupid. Well, I'm not. Look at here. A1 is modified. Look here, A2 is modified. So what is the issue? Remember, process 1 and the process 2 are running concurrently. So they may run in parallel or in the living way. In this example, I will use statement level execution. It means after executing one statement, the next statement will execute. Now look at the answer is here. We have some problem. Now let's say, suppose A1 executes first. When A1 executes, A1 picks up value A0, which is 3, A0 is 3, and process 1 picks up A1, which is 4. Okay, so 3 plus 4 is 7. 7 will be saved to A1. So when process 1 completes, array of A would be 3, 7, and 5. This is the situation before process 2 starts. What if process 2 starts after? Process 2 will see that A1 is 7, A2 is 5. The sum of A1 and A2 would be 12. 12 would be saved to A2. Therefore, when process 2 finishes, array A would be 3, 7, and 12. Is this a correct value? Not entirely sure. What if process 2 starts first, followed by A1, process 1? Process 2 would see A1 being 4, A2 being 5, so 4 plus 5 is 9, which will be saved to A2. So when process 2 finishes its execution, array A will be 3, not modified, 4, not modified, and A2 is 9. And then process 1 starts. Process 1 will see 3, 4, and 9. Process 1 picks 3 and 4 and add them together and put it back to A1. So the result would be 3, 7, and 9. So because we don't know which one of process 1 and process 2 would execute first, if the system is so graceful, allowing process 1 to start, after process 1 completes, the system execute process 2, the answer will be 3, 7, 12. Now, if you run this program again on a different system or even on the same system, and if this system, however, runs process 2 first, followed by process 1, you'll have 3, 7, and 9. Which one is correct? Apparently, both could be correct. This correctness depends on who runs first, and that's a big problem. Because who runs first is something out of our control. It's controlled by the CPU scheduler. Therefore, you have your first taste of non-deterministic answer. It means when we run multiple processes, which would have access to a shared resource, depending on their execution order of their higher level language statement, the results may be different. Therefore, an external factor, which is the CPU scheduling algorithm, dictates what possible answer we would have. Therefore, the results are non-deterministic. An accurate situation can be much worse. For an example, what if, while process 1 is modifying the value of A1, and at the same time, process 2 try to retrieve the value of A1? Okay, so in this case, process 1 and the process 2 execute this statement and this statement at the same time on different CPU cores. We have a big problem. What we have learned so far? Simple. CPU scheduling is not based on higher level language statement. Instead, CPU scheduling happens to machine instructions. So when we talk about this non-determinism, we should not rely on higher level language statement. We have to look at machine instructions. Okay, so let's take a look at an even simpler example. This is so simple. We have a common variable, shared variable count, initialized to 10. Now, process 1 is 1 to it. Process 2, subtract 1 from it. Now, I have a challenging question here. What would be the final value of count? 9, 10, or 11? Unfortunately, if you have a sequential mind, your mind is always fixated to higher level language statement. Your answer is probably 10. Think about it. Let me say it again. If your mindset is fixed to sequential execution, then the answer to my question is always 10. And some of you may have some doubt based on the previous example. How come I would have a 9er, 11er? Are they obtainable? I will show you, yes. But first thing first, you have to disregard higher level language statements, because higher level language statements are not atomic. Remember, what is the meaning of atomic? Atomic means only one can do things at a time, right? Please check atomic instruction slides we talked about earlier. So compiler, when they compile the program for process 1, compiler will translate count plus plus to a number of instructions. The compiler will do the same when they translate count minus to some instructions. I will use a hypothetical assembly language instruction or machine instruction. It looks like this. Process 1 loads the value of count to a register. So the register has the value 1 and add 1 to it. So the register after adding 1 would be 11. After you get the add instruction finished, the register has the value, which is 11, then save it to count. That's from the perspective of process 1. What if we switch the viewpoint for process 2? Process 2 loads the value of count, which is 10, into register. Now the register has the value 10. Then subtract 1 from it. So the register has the value 9. Then save it to count. So in this way, count would have 9, right? So instantly, you notice something very interesting. Because in this example, if process 1 runs this way, it's 11, and process 2 runs this way, along it would be 9. How come that could happen? Now, always remember, interrupt could occur at any unexpected time, could occur here, or here, here, or here. So when an interrupt occurs, the currently executing program will be suspended. The CPU will be given back to the kernel in order to process that interrupts. And finally, when the control transfers back to a process, that process may not be process 1, it could be process 2. So in other words, we may have context switches here, 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 or here. Once a context switch occurs, the other process could get the CPU and do some computation that could affect this process results. The results could also become non-deterministic. So this is referred to instruction level execution, because the execution could switch here, 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 rather than at the end of a higher level language statement. So let's see what would really happen. This table is referred to as an execution sequence. This is a simple one. In your exam 1, exam 2, and in your final, you have to present your multi-processes or multi-threaded execution in this way. That is, using execution sequences. Here, the left half is the execution of process 1. The right half is the execution of process 2. So for each process, I list the instruction in one column, the register value in the second column, and the memory contents in the third column. Remember, the memory is the variable count. It's shared by process 1 and process 2. Now, please follow me. If the CPU scheduler picks process 1 to run first, then process 1 loads the value of count in memory, which is 10, into the register. So from process 1's point of view, after the execution of load, process 1 believes that memory has 10. Register also has 10. So far, so good. But what if a context switch occurs here? The CPU scheduler gives the control to process B. And process B starts its execution of count minus minus. Because process 1 did not change the value of 10, so process 1 loads the count value of 10 into register. Well, process 2 has the value of 10 in its register, and then subtract 1 from it. Right at this moment, you need to know or remember the concept of register. Let's use this as a division line. When process 1 is switched out, process 1 has its register 10. When process 2 is switched out, process 2 has its register value 9. Do these two value 10 or 9 have some conflict? No. Remember, the register value of a process will be saved to the process control block when that process is switched out, and will be switched in and restore the value back to the register when that process resumes its execution. Therefore, at this point, the value of the register 10 will be saved to the process control block of process 1. And when process 2 is switched out, the value of 9 will be saved to the process control block of process 2. Now, at this point, process 2 is switched out, and process 1 is switched back in. So everything we saved when process 1 was switched out would be reloaded back into the register. So before the execution of this add, the register value is 10. Adding 1 to it would become 11. And then process 1 save this 11 back to memory, making the variable count to become 11. So far, so good. Now, what if after the execution of the store instruction of process 1, process 2 is switched back? So at this point, the system would reload the saved register value back to process 2's register. So process 2 will get 9, then process 2 execute the store. The value of 9 will be saved to count, overwriting the previously saved value 11 by process 1. Therefore, this execution sequence shows you that in instruction level interleaving, count plus plus, count minus minus could yield a value of 9 because we have context switches occur here and here. Now, always remember when I list the register value here, this register is different from this register because this register is the register in the context of process 1. And this register is in the context of process 2. They are different things. When process 1 switched out, 10 is saved to its PCB. When this reload back, switched in, the original value will be reloaded back to the register. So we see one thing, possible value will be 9. Isn't it a surprise? Well, if we switch this 2 instruction, you get 11, isn't it? So process 1 is switched out after adding 1 to the register. So by the time process 1 is switched out, the register has 11, memory has 10. Now process 2 start execution, load 10 into register and subtract 1 from it and save it to 9. So at this point, count in memory is 9. Now, if at this point, process 2 is switched out and control is given back to process 1 by the CPU scheduler, the CPU scheduler would reload the context of process 1 back to the register. Therefore, when process 1 starts execution, it seizes the value in the registers being 11 and save it to memory. So this 11 overwrites the value of 9 saved by process 2. Again, we are using instruction level interleaving. Context switch here, context switch here. So isn't it all 3 values, 9, 10, and 11 are possible? That is because context switch could occur at any point between 2 machine instructions. So let's define in a not so rigorous way for what a race condition is. A race condition occurs if 2 or more processes or threads manipulate a shared resource concurrently. So this is the first bullet, the precondition for a race condition to occur. We need 2 or more processes. If you have only one process or one thread, they execute in an independent way. No race condition would occur. Now, the second one is they manipulate the shared resource. That is, this resource is being shared by these processes or threads. They share this resource in a concurrent way. That is, these processes or threads uses or modify the shared resource in a machine instruction interleaving way. And with this pre-assumption, if the outcome of the execution depends on the order in which the access takes place, In the previous example, we have two processes. They manipulate the shared resource, the counter variable, concurrently, because those instructions of those two processes execute in an interleaved way. The outcome depends on order of execution. Of course, we have a 10 if process 1 finishes first, followed by process 2, or process 2 finishes first, followed by process 1. But we could also use machine instruction interleaving to get 9 and 11. So a race condition occurs, let me repeat, if two or more processes or thread manipulate the shared resource concurrently, that's our assumption, and the outcome of the execution depends on the order in which the access takes place. So two or more processes, first key point. Second, they share something. Third, that something is being shared in a concurrent way. If the execution depends on the order of the machine instruction, then we have a race condition. So this is the most fundamental issue in concurrent access. How to solve it? We need the concept of synchronization. From here now and on, I will explain synchronization and how we can prevent race conditions from happening. So please remember, synchronization is a difficult topic. Don't miss class. Otherwise, you will miss a whole lot of things. Just go through my slides usually won't help because I will inject some of my experience and sort of things like that in the discussion. So I have a few notes about execution sequence. You must always use instruction level interleaving to demonstrate the existence of race condition, because higher level language statements are not atomic and they can be switched in the middle of execution. Reason? Because higher level language statements are translated to machine instructions, and the context switch occurs between instructions, machine instruction, rather than between higher level language statements. So instruction level interleaving can show clearly the sharing of a resource among processes and the threads. Now, if you want to show me an algorithm could have a race condition, then you need two execution sequences to do that. Why? Remember this definition. The outcome of the execution depends on the order in which the access takes place. What does that mean? The outcome will be different. If you go through one execution sequence, you have the answer 9, then you have to show me you could have a second different output, say 11. So isn't that you need two execution sequences, each of which produces a different answer? That's the key point. Many of you simply forget it. So quickly go through it. You must use instruction level interleaving because context switches occur between machine instructions rather than higher level language statements. You also need two execution sequences to demonstrate that you have race condition, generating non-deterministic answer. Now, let's take a look at example 1 at the very beginning of this lecture, process 1 and process 2. So suppose you want to say, okay, I have two different answers. First of all, we have two processes. They access a shared resource, and the answer could be different, 3, 7, 12, 379. Therefore, I have a race condition. Not so fast. Remember, the definition of race condition requires you to have two or more processes that share a common resources. But is this common resource being shared concurrently? I'm sorry, I have to tell you that no. Look at execution sequence 1. Process 1 finishes execution. Process 2 starts. In execution sequence, process 2 uses the resource and then terminates, and process 1 starts using it. So in both execution sequences, process 1 and process 2 never access the shared resource, which is the array A, in a concurrent way. Process 1 finishes use it, then process 2 uses it. In this way, process 2 finishes use it, and then process 1 uses it. They never access this resource in a concurrent way. Actually, they use just this resource separately. Now, look at the execution sequence for the counter. Now, look at here. This is process 1, load, add, store. Process 2, load, subtract, store. In this period, going from here to here, process 1 and process 2 are using variable count concurrently. See, use it, and switched out, use it, switched out, use it. So both processes use the common variable count in an interleaved way. Do you see that? So this example fits all required conditions. 1, we have 2 processes, and 2, they share a common resource, and they share it in an interleaved way or concurrent way. And furthermore, switching these 2 store instructions, we could either get 9 or 11. The outcome would be different if the instruction would run slightly differently. So this execution sequence, you need 2, 1 to generate 9, and you show a second execution sequence which shows 11. You need 2 execution sequences to convince me that you have different answer if the execution order is changed. Okay, then we are going to attack this race condition problem. So in order to avoid race condition, one thing we have to be aware of it is those contexts which could occur at any time while I am using a common or a shared resource concurrently. Therefore, if we could exclude this concurrent sharing, we might be able to get rid of race condition. So the first step is, let's define the concept of critical section. I normally would say CS, but I try not to. A critical section is a section of code in which a process accesses shared resources. Now look at this program. I have 3 processes. Process 1, process 2, process 3. We have a shared variable probably in shared memory, count. Process 1, try to add 1 to it. Process 2, subtract 1 from it. Process 3 simply prints the value out. So in these 3 processes, each of which has a statement that accesses this shared resource. So these are critical sections. because count is a shared resource. And in each of this frame, the process accesses the common or the shared resource. It's very simple. You just use a pencil or a marker and simply highlight it. Of course, if you have multiple shared variables, say you have a sum, then process 1, process 2, and process 3 may also have access to a common variable sum. Then you have to circle it out. It probably use a different color. Okay, so what is mutual exclusion? The concept of mutual exclusion is, first of all, the ultimate goal is avoiding race condition. If the execution of critical section is executed in a mutually exclusive way, then every access within a critical section is mutually exclusive. So what does that mean by mutually exclusive? It means at any time, at most one process can be in its critical section. So let's get to here. If the execution, we have 3 critical sections here. If mutual exclusion is satisfied for the variable count, even though process 1, process 2, and process 3 are running concurrently or even in parallel, at any moment, only one of these processes could have access to this one. Oh, that's COUT. This one or this one. So of these 3 processes, only one would have a chance to touch the common variable count. So in that way, we will say these 3 processes access the critical section in a mutually exclusive way. The so-called critical section problem is to design a protocol. With this protocol, processes can use cooperative and ensure mutual exclusion. That is, we are going to add something before we get into a critical section, and also after we get out of a critical section, so that at any moment, there will be no more than one process could be in one of these 3 critical sections. This is the critical section problem. Now, return to a diagram I just mentioned. This is my critical section. We need to add some statement here. We call it entry section. We also need to add some statements here, exit section. The entry section and the exit section would jointly implement the mutual exclusion requirement. That is, for each critical section for the same variable, say count, we have entry section here, exit sections here, so that these 2 sections would work together to make sure at any time there is at most one process could be in the critical section that corresponds to the same commonly shared variable. So before we could implement it, which will be in the next segment, we know we need to solve the mutual exclusion problem. That is, make sure at any moment there is only one process or no more than one process that could be in a particular critical section. So there could be so many ways to add statement to the entry section and to the exit section. Some of the solutions are good, some are not so good. Of course, We as computer scientists, we want good solutions rather than those poor solutions. So what does that mean by a good solution to the critical problem? A good solution must satisfy the following three conditions. The first one is, of course, mutual exclusion. If you fail to do that, your solution is not even a solution at all. The next two would be the progress condition and the bounded weighting condition. Let me remind you, in reality, most of the tools in hand may only be able to satisfy mutual exclusion. They may not satisfy progress and the bounded weighting. You need some extra work to make these two working. But in this unit and next unit, we focus on the theoretical aspect. So we have to make sure all three conditions should be satisfied. And furthermore, in addition to satisfying these three conditions, your solution cannot depend on the CPU's speed and the timing and scheduling policy and so on and so forth, which means the solution its correctness has to be intrinsic. It should not depend on any external factor. CPU speed is an external factor. Timing when you run your program is an external factor. Scheduling, CPU scheduling policy is, of course. These external factors are not factors that can be controlled by you, the designer of a good mutual exclusion solution. So let's review each of these three conditions. First of all, let's re-examine mutual exclusion. It means if a process P is executing in its critical section, no other processes can be executing in their corresponding critical section. What does that mean by the corresponding critical section? If you have a shared variable count, you circled it out, making it as a critical section. Then all processes in which you use the variable count belongs to the critical section associated with variable count. So that means if P is using the shared variable count, no other processes could use it. Now, this assumes that you circle all statements in which you use the variable. If you miss one, I'm sorry. While a process is using variable count in its own critical section, some other process in which you missed the use of count could use count at the same time, and you have big trouble. So the entry section should be able to block processes that wish to enter, but should not. It means if P is in the critical section, what if other processes try to enter its own critical section with respect to the same variable? The entry section should somehow, in a magic way, block them from entering. And what is the use of the exit section? When the process that's executing in the critical section exits, well, upon exit, the critical section has no processes there and should be available to other processes that wish to enter. So the exit section must find some way to report this fact to the entry section so that the entry section would allow a process to get in. Keep this in mind, the entry section should only allow one and only one process to get in. So this is the meaning of mutual exclusion. Simply put, Mutual exclusion is to ensure if a process is in its critical section, no other processes could be in their own critical section with respect to the same shared variable. The entry section should block a process from entering if the critical section is occupied by other processes. Upon exit of a process, the exit section must be able to inform the entry section so that the entry section would be able to allow one process and only one process to enter. Now, the condition, the process condition is sometimes kind of confusing to some students based on my experience. So listen very carefully. Now, what if we have the following scenario? There is no process executing in its critical section. That is, the critical section is empty. But some processes want to enter. Okay, this is the precondition. No one is in the critical section, but several processes are waiting to enter. Based on what we said about mutual exclusion, the protocol must be able to select one and only one to enter, right? So if we have this scenario, the following two bullets must satisfy in order to satisfy the progress condition. One, because we have so many processes waiting to enter. So the first condition says, only those processes that are waiting to enter can participate in the competition. Competing for what? To get into the critical section. And no other processes can influence this decision. That is, I usually use this not so polite example. Suppose you want to get into a restroom because nature is calling. Currently, 3 people are waiting to enter, or 3 people are waiting to enter that available restroom. So the first condition states that only you, those 3 waiting to enter student, can make sure who of you can enter. So suppose student A, B, and C are waiting to enter the restroom, which is now empty. Only student A, B, and C can make this decision for who can enter. No other processes can influence this decision. That is, some other students say student D, who's not waiting, maybe he is in his dormitory. As long as he is not one of the waiting one, he has nothing to say or can influence this decision. So let's get back to the beginning. If the critical section, the restroom is empty, and some processes are waiting to enter, so bullet 1 states that only those who are waiting to enter can make a decision to select a candidate to enter. Those who are not waiting should not have any way to influence this decision. Now, the second one is very interesting. Let me show you the restroom as an example. Suppose students A and B and C are waiting to use that restroom, but the restroom is locked some time ago by student D, who is in the class. Can you enter that? No, definitely you cannot, because that guy locked the door, which means that guy has influence upon the decision. No matter student A, B, or C will select which one to enter, you just cannot enter. Okay, so because bullet 1 states that those who are waiting must make a decision to select a candidate to enter. The second bullet states that this decision cannot be postponed indefinitely. That is, you make a selection of a candidate. This decision determining which one can enter must be done in finite time. Therefore, in finite time, one of the waiting processes will be able to enter the critical section. So quickly repeat. The progress condition states that if currently a critical section is empty, but some processes are waiting to enter, then 2 conditions must satisfy in order to satisfy the progress condition. First one states only those who are waiting to enter can select a candidate to enter, and no other processes, that is those who are not waiting, can have any influence upon this decision. The second bullet says that the decision time has to be finite. What is finite? You could write an integer as long as you could write down that integer with finite number of digits. That is finite. So an algorithm satisfies progress must satisfy bullet 1 and bullet 2 when there's no one in this critical section. Now, some of you may be confused between progress and bounded waiting. So listen to me regarding bounded waiting very, very carefully. The progress condition states that the critical section is empty, but some processes are waiting. So the progress condition is about the decision to select a candidate. So that is a group decision time. Bounded waiting, however, is about each and every single process rather than the group that are waiting. So bounded waiting states that after a process made a request to enter its critical section, and before it is granted the permission to enter, there exists a bound on the number of turns that other processes are allowed to enter. Well, that looks like a bit too wordy. Simply put, first of all, we need to know the bound. We need a bound. Suppose I want to enter a critical section, and then I participate in the competition to enter. If the bound is 3, then I failed the first time because I was not selected to enter. I failed the first time. So one process is ahead of me. Then that process exits, making the critical section empty. The protocol, the enter protocol, knows the critical section is empty, then I am still there waiting. So all of the waiting processes would compete again, eventually to get a candidate to enter. So what if I failed again? So in that way, I have 2 processes ahead of me. That is, I wait for 2 turns. Now, if the bound is 3, that means I wait for at the most 3 turns. So that means somebody will be ahead of me. Then the 4th time, when I participate the competition again, I get it. Hope you understand that. So let's get back to the restroom example. Student A, B, and C. are competing to get into the restroom. So one of them will be selected, let's say student C. And let's say the bound is 4. Student C is using it. So from student A and the student B's point of view, both of them wait for 1 round. And then a student C exit, a student X comes in, waiting to enter. So upon exit of student C, student A, B, and X are waiting to enter. Then they compete to enter. One candidate is selected. Well, the candidate could be, say, student B. So student B, after waiting for 1 round, at the second round, he could enter. So the number of turns student B has waited is 1. So for student A, if he is lucky, the third competition, he could get in. So student A could enter after waiting for 2 rounds. Now student X has waited for 2 because student X comes in after student C exit. And then student B enters the second round and student A enters. So student X has waited for 3 rounds. No matter what, if the bound is 3, even though student A or B or some student Y or Z comes in, student X could enter. So that means we need to have a bound, a predetermined value. This bound means how many turns or how many rounds I have to wait. So there exists a bound on the number of turns that other processes are allowed to enter. If the bound is 3, ahead of me, there are 3 processes could enter. Whether these 3 processes are the same or different, doesn't matter. So a bound is definitely an integer, a value, right? So some of you usually could not distinguish the meaning of bound and finite. Always remember, finite is not the same as bounded. Bounded is a value, I know. The number of turns I have to wait cannot exceed that value. A value I know beforehand. I know directly from the algorithm. But finite is any number you can write down. So if the bound is 3, it's definitely finite. But finite is not bounded. Okay, because finite, as long as you could write down a finite number, you add 1 to it, the result is still finite, but maybe unbounded. Okay, always keep this in mind. But what is the values bound? Well, you have to study the algorithm to find the bound. Furthermore, the value bound is usually a variable of how many processes are involved in the competition. Just like when you study data structure, you learn how many comparisons are needed for a sorting algorithm. For example, bubble sort, insertion sort, and worst case of quick sort is of the order n squared, where n is the number of elements. So if your system has n processes participating in a concurrent work, and you need some critical section to ensure mutual exclusion in order to avoid race condition. So the bound has to be a function of n, the number of participating processes. Remember this, but in the next unit, we only study 2 algorithms to solve the critical section problem. Therefore, the bound, you can find is always a constant, a function of 2. And this function has to be constant. So let's review what we have learned here versus progress versus bounded waiting. Progress does not imply bounded waiting. Reason is very simple. Process is a group decision issue. Bounded waiting is for each process. The process condition says that a process can enter the critical section within a finite decision time. This finite decision time could be very long, 1,000,000 years, 1,000,000,000,000 years, and so on. It does not say which process can enter. It just says only one process will enter, but we don't know which one. And there's no guarantee for bounded waiting. That is, I only select a process to enter. I am not able to guarantee you a particular process would wait for, say, 5 runs. So progress does not say anything about bounded waiting. Conversely, bounded waiting does not imply progress either, even though we have a bound, saying that every process only wait for 3 runs before it can enter. All processes may be locked up in the enter section forever, which means the decision-making in the progress condition could be infinite. Of course, this is definitely not a good algorithm. Therefore, progress condition and the bounded waiting condition are independent of each other. So a good solution to the critical section problem must satisfy 3 conditions: mutual exclusion, progress, and the bounded waiting. Now, we need to introduce a few related terms. I left most of them for you to read. Sometimes we see deadlock freedom. That's deadlock free. A solution to the critical section problem is deadlock free. If 2 or more processes are trying to enter their critical section, one of them will eventually enter. This is the progress condition without outsider having no influence. Remember, the first part in the progress condition says that if the critical section is empty and several processes are waiting to enter, in finite time, we are able to select one candidate to enter. Those who are not waiting will not influence this decision. So deadlock free only says in finite time, we can select a candidate. It does not say those who are not waiting will not have any influence. So basically, the progress condition is stronger than the deadlock free condition. And then please read our bounded waiting and find first in, first out. Okay, let's move to starvation free or starvation freedom. It says that if a process is trying to enter its critical section, it will eventually enter. It means I don't have a bound. If I want to enter, no matter how many times I participate in the candidate selection in the progress condition, I eventually enter. So it means I may have to wait for 1,000,000 times, 1,000,000,000 times, 1,000,000,000,000 times, eventually I can enter. Which also means it's weaker than the bounded waiting condition, because the bounded waiting condition has a bound. I do not have to wait for more than that number of times. In starvation free, I just say, I eventually can enter. It could be 1,000,000 years. So I have several questions for you to think about before I conclude this unit. Does starvation free imply deadlock free? Second, Does starvation implies bounded waiting? Of course it's not. We just mentioned it. Third question, does bounded waiting imply starvation free? Yes, of course. Now, does bounded waiting and the deadlock free imply starvation free? Okay, these are the questions for you to think about. Okay, the answer is here. Please go through it. Then, this is the end of this unit, because this unit is very, very difficult. And the information provided in this unit is very extensive, requires you to think deeply. So I welcome you to ask questions. When you ask questions, either by email or by use of Zoom, please read the slides first. And if you do have problem or do have question regarding certain slides, make sure you will tell me which slides you are referring to so that I could bring up the slides and answer your question. So that's the end of this unit. Happy doing mutual exclusion and happy to accept this challenge. Goodbye.